Alright, so in this video we're going to talk about the reliability of measurements, and specifically how we can tell how reliable different measurements are. This is going to start on page 14, and then we're going to jump to page 16 to finish up the notes in this video, and then when you're done with that, you're going to come back to page 15 to do the practice problems that go along with these notes. So let's jump in. At the top of page 14, you should see the words accurate and precise, or accuracy and precision. And these are two words that are often used interchangeably out in the world, but to scientists they do have distinctly different definitions, and it's important we understand that before we start talking about how these affect and apply to our measurements. So accuracy is how closely the measured value is to the actual value. Sometimes I think of being accurate as being accurate. It's all about hitting that right value and the goal, the target. Precision, on the other hand, is how close a series of measurements are to each other. So you don't have to be right, you just have to be close to the other measurements that you've made. And as you can kind of tell, you'd have to make repeated measurements to be able to be precise. One single lucky shot could be accurate, but it doesn't really show the same level of skill as precision. So you can be one or the other, but of course the best measurements would be both accurate and precise. So how can we measure and compare accuracy? Well, we're going to use percent error, this equation. And before you get too worried about this big, kind of weird looking equation, this is on your equation sheet. You will not have to memorize this for any tests or quizzes. It will always be there. You just need to be able to pick out what numbers in the problem you need to plug into these places and be able to put it into the calculator to get that answer. So let's take a second to look at a couple of things we need to be careful of with this equation. And the first thing I want to point out is that these are absolute value brackets around the subtraction in the top, which means that no matter what this number turns out to be, we're always going to make it positive. That's what absolute value does. Honestly, we don't have these absolute value brackets for a calculator, so you're probably going to end up putting the problem into the calculator with parentheses instead of absolute value brackets. Just remember to get rid of any negative signs that pop up, and that's going to take care of that for you. And the only other thing that we really need to notice is that we have two different types of values we're plugging in here. The accepted value and the experimental. The accepted value is always going to be what you should have or could have gotten, the right value. Then the experimental value is what it sounds like. It's maybe not perfect, it's not what we should have or could have gotten, but it was my best attempt in the lab, in an experiment. That's what the student or the teacher experimentally got, even if it's not perfect. And so notice we're taking that difference on top, that subtraction there, to find the difference between what was right and what I did. And then we divide by that accepted value. It kind of scales that value, puts it in some context for the size of that value. And then, of course, we multiply by 100 with all percents. So let's look at a couple of problems real quick and practice this. And this really is kind of like grading your work in the lab. So the first example we're going to look at here is like finding a grade on a test. The most important thing here, we've got two numbers in this problem, and it's really important that we use the correct one as our accepted and the correct one as our experimental. So ask yourself when we look at these numbers, is this what should have or could have happened? Or is this an experimental determinant that maybe not isn't perfect? So this says there's 34 questions on a test. Johnny answered 22 of them correctly. What's his percent error? So the 34 questions on the test is what he should have or could have gotten right, which means that's our accepted value. And his experimental attempt at answering questions on the test resulted in 22 of them getting answered correctly. Well, that doesn't seem too shabby. Let's see what this turns out to be. If we plug that in, we've got our accepted minus our experimental, and absolute values, of course, all over our accepted and times 100. I'm just labeling my numbers and then plugging them in where they belong in our equation. Now at this point, if you want to plug this all into your calculator in one go and just push enter equals once to get an answer, you've got to be really careful to remember to put these top subtraction numbers in parentheses. You will not find an absolute value bracket in your calculator to use. Use parentheses and you'll be fine. If you don't want to remember to do parentheses, you just need to force this to go through the correct order of operations, which would mean that you would probably want to start by doing that subtraction there. 34 minus 22 is 12. That's still going to be divided by 34 and multiplied by 100. So I did one little subtraction, taking these numbers and turning it into that. And now I can finish this out with putting it in my calculator, which would get me the unrounded answer of 35.2941. Because all of my numbers in my problem were 2 sig figs, I'm going to keep 2 sig figs in my answer. And 35% is my answer. Now, keep in mind, this isn't his score on the test. This is his percent error. So this is how much of the test he made an error on. So it's really not that he earned a 35%. It's really the opposite. He earned a 65% because 35% of his test was completed in error and incorrectly. So that's what this tells us. Looking at this next problem, remember to find our E and our A. I actually want to give you a second to try this on your own, just to find your E and A. Ask yourself, is this number something that could have happened, the perfect number, the goal, or was this somebody's experimental attempt at making a measurement? So we've got our two numbers, and because the label says the rope is 2.15, that's the accepted value. That's what it should be. Then John tried to measure it, and he came up with 1.85. So that was his experimental attempt at measuring the rope. And so now we just start plugging things in to our equation, taking our starting with A, minus our E, absolute values, over our A, and times 100. Once again, if you want to plug this in all at once in your calculator and just push enter once, you can absolutely do that. Just make sure to use parentheses up top here. And if you do, then this should tell you your answer is 13.9534 coming out. If you want to do this in 2 steps still, do it just like we did last time. Do that subtraction, write that down, it's 0.3. And then do your division multiplying by 100, and you should get the same unrounded answer. At this point, we need to round it. Both of our numbers in our problem had 3 sig figs, so we're going to keep these 3 sig figs here. But that 5 is going to round my 9 up, which is going to round my 3 up. So it is actually going to end up changing to 14.0 as my 3 sig fig answer. And, of course, percent would be my units on that answer. Hopefully this percent error stuff isn't too bad. Remember, I'm giving you the equation. The biggest thing is just decide which is your E, which is your A, and then make sure you're comfortable plugging that into the calculator. Now we're going to talk about scientific notation. And I know there's some stuff that says scientific notation at the bottom of page 14, but that is a little bit extra and way too big. All of these steps and instructions for scientific notation are on page 16. So we're just going to redraw that little A times 10 to the B thing that was at the bottom of page 14 in whatever little space you have at the top of page 16. Because I do want to make sure that you know what these words are called. Because scientific notation, if you weren't always aware, is this way of writing numbers with this times 10 in them, where we're going to get rid of digits that aren't sig figs. So essentially what that's doing is taking a really big number or a really small number that have lots of these extra zeros that don't count as sig figs and getting rid of them. Because if they're not significant, they don't add anything to the accuracy, precision of our measurement, why would I spend all my time writing them, and let alone counting them so I can write the right number of zeros over and over again? Scientific notation is a way of taking those huge numbers or tiny numbers with all those zeros and making them more manageable to read and kind of share with each other. So when talking about scientific notation, the number that's before the times 10 is what we call the coefficient, or sometimes the base. And then the exponent, the B part here, is the exponent on the times 10. And that's going to be a really important number. Both of them are important, but let's talk about how we get these numbers for any specific value that we're trying to turn into scientific notation. There we go. So we've got our process written down for you here. And the first step is to put and move the decimal to be after the first non-zero digit. And that's really important. There are other standard ways to write numbers that look like scientific notation, but proper scientific notation will always have the decimal after the first non-zero digit. No, let me get rid of that circle. So we always move this to a specific place, and then we find all significant figures, because we want to get rid of any zeros that aren't significant figures. So that's kind of setting up the A part here, moving the decimal into the right place and getting rid of any extra numbers. Then we're going to start trying to figure out what the B is, what that exponent is on the 10. And to find that, we're going to count how many times the decimal has to move to get from it where it started to where we put it in step 1. And however many times that decimal moves is going to become our exponent on the times 10. We have to be careful of this sign. I know there are some tricks and some things online that help people with scientific notation about like left is positive, right is negative, or vice versa. I honestly can't keep it straight because the decimal moves different directions whether you're going into or out of scientific notation. And so those rules have never really made sense to me because they don't apply to every situation. So this is the best way I've found over the years to remember it, is if that original number in its standard form is larger than 1, then the exponent is positive. Because plus generally means more or bigger and positive. If the original number is smaller than 1, then the exponent is going to be negative. So we move the decimal, count how many times it had to move, and then make that a positive or negative number on our times 10. It really shouldn't be too hard, but every step there has places where you can go wrong. So we've got to be careful in how we do it. Let's look at some examples. The first step is to put my decimal where it belongs after the first non-zero digit, and that's moving left to right. So the first non-zero digit I see here is 3. So I'm going to put my decimal after that 3. Now we're going to try and assess our sig figs. Are any of these zeros sig figs? Originally, no, because those trailing zeros didn't have a decimal in them, not until I just moved it and added it there. So those aren't going to come with us. That means that our base, our A part of the scientific notation is just going to be 3. With a decimal or without, doesn't matter. Then we always have the times 10 part. And now let's find that exponent. The exponent is going to be how many times our decimal moved to get to this new spot. And even though we didn't write that decimal, and it's important that we didn't because we want to get rid of these zeros, keep in mind it's always understood to be at the end of a number if it's not visible, if it wasn't written. So it is here at the end of our number, and we have to move it 1, 2, 3, 4, 5, 6 times. So our exponent is going to be a 6, and it is going to stay a positive 6 because this original number, 3 million, is greater than 1. So bigger than means positive exponent. With this next example, remember we're reading left to right, and we're going to put our decimal after the first non-zero digit. So that's going to go after the 6. And the only zeros we can get rid of here are these 3 leading zeros. This sandwich 0 and this trailing 0 are sig figs. Remember, trailing zeros are sig figs if there's a decimal in that original number, which there is. So this is going to be my base now, 6.030. Put my times 10 there, and then count how many times it had to move. This time I saw it here, and I had to move it 1, 2, 3 times to get it into its new spot. But because this number, 0.006030, the original number in standard form, is less than 1, I'm going to make that a negative 3. Keeping going, putting my decimal after the first non-zero digit, getting rid of digits that are not sig figs, use my base as 1.2. And then this is going to be times 10 to the negative, because this is definitely a small number. 1, 2, 3, 4, 5, 6, 7. So this is going to be 1.2 times 10 to the negative 7. I'm going to do one last example for you, and then I want you to try those last two with on your own. Maybe compare it with the people around you. Move my decimal after the first non-zero digit. Getting rid of any zeros that aren't sig figs means my base, my coefficient is going to be 8.79. Then I add the times 10 part, and this must have been at the end. 1, 2, 3, 4. And this number is definitely larger than 1, so we'll leave it as a positive 4. So I can tell you the exponents on these last two are going to be negative, because I can definitely tell these are both smaller than 1 numbers, but they're not going to be the same number, but they will both be negative. So at this point, we've finished the notes that I need you to do in your packet. So now it's time to flip back over to page 15. You'll notice some percent error questions at the top, some scientific notation questions at the bottom. Knock those out, check them. If you have any questions, make a note of it, and I will help you next time in class. So, hope that wasn't too bad.